integral from a to b of some f of x, right, equals what we say, some big F of x, right, evaluated from a to b, and then we further say that this evaluation means to take the big F function at b, right, and subtract the big F function at a. Right, so the issue really is, if we're going to follow this rule, when does the rule apply? What kind of functions make sense for this? So what are the restrictions on this? I was really surprised actually when the kids immediately started speaking up in the last class. If you had it like you had the definition memorized, I was like, wow, I don't even know if I know what that was. It's pretty cool to hear. What are the restrictions? What has to be true? Basically, about the function itself and about a and b.
They have to be differentiable. I mean, continuous.
Okay. Yeah. F continuous, and usually they say and differentiable. This being the big issue here. And what? Over the integral that we're interested in. Right. So basically what? On some a, b interval. What's therefore true about a and b? That'd be real numbers. Yeah, that's one way of putting it, that it's an element of the real numbers. Probably a clearer way for some folks in terms of this issue is that these are not plus or minus infinite. They have to be actual numbers. Don't forget, infinity is not really a number, right? It's really a concept that we have a symbol for. It's not like 15. Like what's 2 times infinity? It's not 2 infinities. It's still just infinity. So 2 times 15 doesn't work that way, right? So this is kind of a very special symbol in a very special case. So the function has to be continuous, meaning what? When you draw the darn thing, you can't pick up your pencil and put it back down, basically, right? I mean, you either, in other words, asymptotes are issues, right? When I draw those, I have to pick up my pencil. When you have what, jump discontinuity. What's the last type? Holes, yeah, and don't cheat and do that. Right? Sure. Right, so those are the kinds of problems with functions, right, that make this rule not work. So don't integrate from here to here. Don't integrate from here to here. Don't integrate from here to here, because this doesn't make sense. It has to be continuous. All right, so what's this about? Well, this is like when we talked about that 1 over x function, where we said, what happens when you go really far out in the tail? And that's where we're going to start again with examples here, with that function. We talked about them different types of these improper integrals. So first example, let's say, if you're asked to find the integral from 1 to infinity of 1 over x dx, we've actually done this before. Right? We know that what we think that we want to do, right, is take this reciprocal function, right, find where 1 is, and just find this value all the way out. The problem, is obviously this issue that we can't have infinite bound here. We have to have some real number, right, for these limits. So what we do is essentially say, well, how can I still get this same thing done, but not have infinity there up in the upper limit? So we think in terms of asking the question in this sense, and that we say, all right, well, what if I took the function, took the boundary at 1, took another boundary at b, found this area using the integral, the integral here from a to b, the f of x dx, but then shove this out to infinity. You know, once I already have an expression for that area up to b, why not then use it with an infinity in there in a limiting sense? Right, so what that makes you do then is essentially take this part of the symbolism, right, the integral from 1 to infinity, and replace it with a limit as b goes to infinity with an integral from 1 to b. All right, so you can say I'm going to go just to b, but then I'm going to shove b out to the side as far as it goes. And just leave the rest as it was. Right, so it's a bit of a pain in the sense that you got to keep writing this thing down over and over and over again as you work out your integral. So some folks actually don't bother; they just keep the infinity up there, and they know that they mean a limit, not really a value and stuff. But at least in a math class, you should write it in the proper notation, which does separate this limit off to the side. All right, so you would write still limit b goes to infinity. This follows through right until the very end. Go ahead and evaluate your integral. So in this case, write the log of the absolute x. All right, write your evaluation 1 to b. So we're at this point here. Everything's legit, right, because of the b being finite. And then do the last part like this, but still keep this limit. B goes to infinity. So what now I'd have in here a log of absolute b minus a log of absolute 1. And then what? It's a matter of, you know what the log of 1 is, I hope. And that's 0. Right? Think about the graph. Talking about that point. And then what? The log function as, your log of b as b goes to infinity is what then? And again, you might just think about this function.
Infinity.
Right, that you never see anybody draw an asymptote, right, like a ceiling. So yeah, it's implied that it continues up. And so certainly then, if we have then an infinity minus 0, or infinity as an answer.